This is the second part of the lecture of 21st of October, and we are starting with questions of students. So please, you have a question?
In this case, we simplified the system with the vector and matrices, but then it was only an example because we didn't use them.
We shall use. This is very important question because she observed that practically we didn't use this. Actually, the purpose is to write, after a while we shall see, to write our simpler system in matrix form, then to find eigenvalues, and then to decide the behavior without making all these calculations that we did in details, very long calculations. So when you know the matrix, the received shall be find eigenvalues, and on the basis of these eigenvalues, we can see what is the picture without solving like this. So we shall use this. For the moment, we simply mentioned that we can rewrite our system in simplified form. Okay. Other questions? Thank you for this question. This is interesting. Let us see if there are some other questions. Please? Please, no, don't worry.
I didn't get why we put the constant that is dependent on the time, and we didn't consider the e related to the t. I didn't get why.
Okay. This is a very important method of varying the constants. So what you are doing, if you have this equation, let me explain you from another point of view, this equation. So you proceed in the following way. First, you say, let us for the moment forget about this guy. If we forget, then we shall have formally, let us, instead of x, use another letter. For example, z is 80 zeta t. So since I promised to cancel this guy, I switched from x to another letter, and I am looking for solution of this equation that usually is called homogeneous. Homogeneous, and this is not homogeneous because you have b. When b is 0, this is called homogeneous. And this is without b, not homogeneous. Why this is simple homogeneous equation? Because we can make a separation of variables. This is a quite simple case. Remind you that we have zeta prime over zeta is a. We can rewrite in this form. We divide by zeta. Look. Divide by zeta, and we have zeta prime over zeta. Zeta prime over zeta is the derivative of logarithm of zeta. So we can take integral in the left and in the right. Take integral here and integral here. This is at dt. This is, we call this d zeta over zeta. And when we take the integral, you obtain logarithm of zeta is primitive at. For simplicity, we call this primitive capital At. Due to the lack of space, if you don't mind, I shall clean a little bit the blackboard in order to explain you better this phenomena. Now, I think, let us for the moment clean this part. All this, and in this way we have more space. So I want to explain what we are doing in this case, and then you shall apply for, shall be more clear what we have done. Okay. So again, we rewrite the equation for zeta prime over zeta equal a. Then we integrate integral d zeta over zeta is integral of a. This is t dt, and we call this is by definition capital AT. We compute the primitive and call one primitive a. So this means this integral is obvious. This is logarithm of zeta is capital A. Please.
When I integrate,
Yes.
doesn't matter if I write the first equation. Yes, I can write also zeta prime over zeta d zeta.
Yes, because this d zeta, usual, this I explained that d zeta typically is zeta prime dt.
Okay.
So you have this convention, mathematical convention, that zeta prime can be connected with d zeta in this way. This is the a formula for changing of variables. If you want, we can practically put here some values and take integrals with given extreme points. For example, I can put here from zeta 0 to zeta of t, and here from 0 to t. Then, when you take logarithm of zeta, the primitive shall be this guy, logarithm of zeta, we said zeta of t, minus logarithm of zeta 0. This is at. And now you can see that this can be solved explicitly from this. Let's see if you can see. Yes. From this we get zeta t divided by zeta 0, because logarithm of zeta minus logarithm of zeta 0 is logarithm of zeta divided by zeta 0. So if I take exponent instead of logarithm, I have to take this to be a to the power at. And in this way, we arrived at our solution, which is from here. We arrive zeta t is zeta 0 a to the power at. So as you can see, our first step is to solve this equation. That formally is not our equation, but is very helpful. Why? Because in this equation, you can immediately recognize one constant. Which is the constant? Zeta 0. And the method of varying constants means that you shall make this constant only depending on t. Varying constant means in order to solve this equation, not this one, you shall use this representation, but you shall assume that this coefficient is not constant, but new function. This explains why we modified only the constant, putting c of t in our previous calculation. And in this way, we can say that this is, if you put in your notes this formula, then you can skip this derivation of the formula. You know that this equation always has this solution, where z0 is a constant, capital A is the primitive of small a. Or if you prefer, we can write as integral from 0 to t of our small a. In our case, this small a was 1. So when we compute capital A, this will become directly t in our example. So we succeed to find our zeta, and now we can go to this formula and say what I did here. I simply used my solution, but instead of zeta, I write x because I'm looking for x. So I put here x. Then a to the power at, when I vary constants, I shall not touch. This constant is important, this exponent is important to cancel in our method, as we have seen the cancellation. You look, this guy is cancelled with the right hand side. This cancellation is important, and we shall not touch exponent. We shall touch only the constant. And the constant really is changed. It is ct. And when you take this substitution, so instead of looking for x, you look for c. And for c, we get very simple equation. We solved it. After this, the method is working by itself. You don't do anything, it is automatic. The important thing is to remember first to switch from non-homogeneous to homogeneous. For homogeneous, to write this solution, if you forgot, open your notebooks, see the solution, put it. If you haven't it, you can do by yourself this calculation. These are 2 lines. But finally, you get this solution with this constant. These are the data of zeta when t is 0. And it is clear that this constant is exactly the constant you need to apply the method of varying the constant. Metodo della variazione dei costanti. This method means that we, in order to solve non-homogeneous equation, we take xt in the form ct, and the exponent we do not touch, because everything is prepared, only vary constant. And then for c, we get very simple equation. We solved c prime equal -1, and we solved it. So this is explanation why we didn't touch this part. This is exactly the method of varying the constant. So thank you for this question. We repeat it. Probably this method we didn't use very deeply in our previous lecture, but now is the time to simplify a little bit the method. And in this way, we can solve these linear equations that appear frequently when we have matrix form. Okay, some other questions? Oh, this was very useful. Some students from internet, do you have some questions? For the moment, I cannot see in chat other questions. Therefore, let us continue. Okay. let us continue with what we have done is essentially two examples, but here we have to build the picture. What is the graphic? We have to build our solution because we found explicit solution. So if you don't mind, I shall leave this part so that you can see our explicit solution, shall clean all the rest, and shall try to build the picture on the right-hand side. Okay. You shall see also in the second part of our course when we have kind of necessity to work with data that has to be analyzed, that we very frequently shall use this coordinate system to represent graphically our abstract solutions or abstract data. Numerical data, we have to put in some graphic. And in our case, the simplest way to build the picture is to take t equals 0, t equal half, t equal 1, build few points, and then to try to connect this point because we expect very continuous curve. We do not expect curve that is very rapidly jumping. In fact, all functions here are very nice differentiable functions. Therefore, let us start. Of course, the first point we know, 1, 1. This is t equals 0. This is our starting point. We said, let us try to take bigger t. For example, t equal 1. What will happen with t equal 1? X shall be 0, epsilon shall be a. Neper number, a is 2.7 something. Therefore, we have x is 0, and this formally is Neper number. So we have this point. This is the time t equals 0. This is the point t equal 1. What we can say for t, for example, 2, what you can say for this guy, x. When t is 2, x becomes negative. So we shall go to the opposite half plane, x negative, and we shall have minus a to the power 2. Therefore, we shall have some point that formally is in this direction. What shall be epsilon? A to the power 2. So we have really point which is t equal 2. This is t equal 1. Probably to have better picture, let us take t equal 1/2. When t is 1/2, here you can use your calculators, for example. This is 1/2, a to the power 1/2. Square root of 2 something. This shall be something between 1 and 2, divided by 2 shall be something smaller than 1. And of course, you shall have here, when you have 1/2, some point, roughly speaking, x shall be here, smaller than 1, while epsilon shall be something bigger than 1. Therefore, as you can see, this is t equal 1/2, and roughly speaking, we can build very rough graphic, but this rough graphic shows that how I shall put the arrow where the time is growing. It is already on the picture. We know that our arrow shall be in this direction, because this is already put on the, we put t equal 1/2, so this is, of course, if you need a better picture, you have to use some software, and you shall build this software, you shall build your picture more precisely. But qualitatively, this is a function that is decreasing in x and increasing in epsilon. In epsilon is always increasing. What you can say about t equal, for example, -1/2? If we have minus t equal -1/2, so if we go in negative time to see the past instead of seeing the future. So when t is -1/2, let us try to build -1/2, this will become 3/2. 3/2 a to the power -1/2. This is 1 over square of 2, so this is slightly bigger than 2. By 3/2, this shall become very big, relatively big x. While epsilon, what we can say is epsilon is going to something smaller than 1. So we have something that should be in this direction. Since I am not sure, I am doing something that one mathematician shall do immediately. What is the limit when t goes to -infinity? If t goes to -infinity, a to the power -infinity is what? 0. If I put -infinity here, shall be +infinity. A to the power -infinity, we have fighting between polynomial and exponential. Exponential always is winning, is stronger. So this is also 0. So this is quite natural that our curve goes like this to 0. When actually I shall not put here the arrow, because arrow was reserved for future time. But I shall put here t equal -infinity to remind me that this is the past. The past, somehow we shall be, when go to the past, we shall be very close to 0. And then our curve, you see how is going. So this is not a graphic of a function, because, you know, function, this means if you take 1x, above this x, this is only 1 epsilon. And this is not the case. Our curve is making this turn, and making this turn, we have, of course, not function of x. But somehow our curve represents solution of our equation. So this is very rough graphic, but more or less shows that we have such rough behavior. I shall not insist when you make your solutions very precise. What I want to see the behavior when t goes to infinity, to have few points on the graphic, and more or less to have a picture that corresponds to the solution you have found. Okay, with this we finished our example, and as you can see, these two examples, they need to compute the exact solution. And this is, in some cases, as you have seen, is not very simple. Okay. Let us now finish our, we have only a few minutes for our short second part movie. Let us finish with a very simple example that shall take only 2-3 minutes. And this is practically let us try to treat our last example that is very significant and shall be used in the future. When you have a system of this form, x prime equal lambda 1 x, epsilon prime equal lambda 2 epsilon. Of course, here lambda 1 and lambda 2 shall be two real numbers. And we consider the case when 1 is positive, lambda 2 is negative. Actually, our first example was very similar to this case because we had one was 1, the other was minus 1. So our initial point is x0 equal x0 and epsilon 0 is epsilon 0. And we want to see geometrically what is our solution, because here we can solve very easily. The first equation, the solution we can find very easy. Xt shall be x0 a to the power lambda 1 t. This was according to our generic formula, when we had x prime equal cx. This we wrote before the break, and this was the solution. Epsilon t shall be epsilon 0 a to the power of lambda 2t. And now we can build roughly the picture. Of course, the first point is x0, epsilon 0. This is the point t equals 0. What we can say for the point when t is 1? We have a to the power lambda 1. This, when lambda 1 is positive, is increasing function. So I have to increase x. While this function, when I have bigger t, shall be smaller epsilon. And this means when I take t equal 1, x shall be bigger, epsilon smaller. What does it mean if you build and divide the plane into 4 pieces? I think we have to be here, because here x is bigger and epsilon is smaller. Not here, because here we have both x and epsilon bigger. Not here, because here we have x smaller, epsilon bigger. This is not our case. Here we have both x and epsilon are smaller, and I need this point. So we have, when t is equal 1, we are somewhere here. And we can, in this case, say that when t is 2, we shall have the next point, but then we are asking, when t goes to infinity, what will happen? Lambda 2 is negative. A to the power minus infinity is perfect 0. while this guy goes to infinity. So x to infinity, epsilon to 0. Where we shall go? Shall go always closer and closer to the xx. And therefore, we shall have this picture. Approximately, our curve shall be in this direction and shall approach x equals 0. What will happen with negative time? With negative time, you can see that we have similar behavior, and we have this part of the picture. This corresponds to t equal minus infinity. This actually was hyperbola that we studied for our first example. Example 1 was hyperbola. This was the case when lambda 1 was 1, lambda 2 was minus 1. But it is the same when we have one positive, one negative eigenvalue. And we shall say that in this case, when one of the eigenvalues, because lambda 1 obviously is your eigenvalue, what is the matrix in this case? If you write like u prime equal a of u, your matrix A is very simple. Lambda 1, 0, 0, lambda 2. So if you want matrix form, it's clear. And lambda 1 is positive, lambda 2 is negative. When you have positive and negative eigenvalue, we always shall have picture of this type. And of course, you can say, oh, what will happen if I move x0, epsilon 0? For example, if I start not from here, but from here, of course, you shall have another guy. And always your picture is like this. And in this case, we shall see that if we are speaking about picture close to 0, this point shall be called saddle point. But this classification we shall do later. Now, I want to say that if we understand well the basic examples, then we can build the picture very simply, moving our initial data, moving our curves, and in this way we build kind of flux of curves. This is like a flux flow that practically each of these curves represents one possible initial data, and again, arrow represents the direction of time. So with this, I want to stop for the moment, as I promised, with 2 minutes delay, to stop my lecture and leave you for the next week time for your questions. So I shall stop the